Welcome everyone. Welcome Eleonora. She will give us a seminar about the X-ray star spectral timing, and she's a PhD student and some in Warsaw. So the floor is yours. Thank you.
Okay, so hello everyone. First of all, I would like to thank you for inviting me to give this talk, this presentation today. So once again, my name is Eleonora Lai, and I am a PhD student at the Nicolaus Copernicus Astronomical Center in Warsaw. And today I will talk about my latest results concerning the study of the stellar wind in Cygnus X-1 and how its variability affects the spectral timing properties of the source. Let's have a look at the outline. So first of all, I will talk about the X-ray binaries and the two particular classes, the low mass X-ray binary and the high mass X-ray binary. Concerning and also the differences in the accretion process between the two classes. Concerning the high mass X-ray binaries, I will talk about the stellar wind. Then I will present the protagonists of my work, the source, Cygnus X-1. So I will talk about its discovery, the stars which compose the system, its energy spectrum, and its variability properties. Then I will present my result, the results of my research. And first of all, I will talk about the power spectrum and what are the effects of the presence of the stellar wind for the variability of the source of Cygnus X-1. Sorry. Then I will talk about the estimate we made for the radial sides of a typical clamp crossing our line of sight, and also about the presence of an accretion bulge for this source. At the end, I will give you a brief overview of what we mean when we say spectral timing and in general spectral timing techniques. Then in particular, I will talk about the two analyses, the intrinsic coherence and the time lags as a function of frequency, and how I made use of these two analyses to constrain the effects of the stellar wind. So what are X-ray binaries? In general, an X-ray binary is the brightest source of X-ray emission in the universe. And it is composed of a compact star that could be a black hole, a neutron star, sorry, or a white dwarf, and a companion star. So compact stars release gravitational energy and emit radiation in the X-ray band by absorbing material transferred from the companion stars. Using different X-ray telescopes and other surveys, but also optical telescopes, scientists were able to detect more than 400 X-ray binaries only in our Milky Way, comprising also the Large Magellanic Cloud and the Small Magellanic Cloud. One way to classify the X-ray binaries is as a function of the nature of the compact object. So if we have an X-ray binary containing a black hole or a neutron star, we have two main classes, the high mass X-ray binaries and the low mass X-ray binaries, depending on the mass of the companion star. But when we have a white dwarf as a compact object, we have several subclasses, depending on their observational properties. But in general, most of the time, we can classify X-ray binaries containing white dwarfs in a main class, namely cataclysmic variables. So for my work, I focused more on this branch, the black hole X-ray binaries, and in particular for the class high mass X-ray binary. But let's have a look also to the low mass X-ray binary class. So low mass X-ray binaries are binary systems in which the companion star can be a main sequence, a subgiant, or a red giant star. So the mass, it's small, it's lower or equal 1 solar mass. And for this reason, it cannot be detected. It's a faint source. In these systems, the compact object accretes via the canonical Roche-Loeb overflow. So any material passing beyond the Roche-Loeb will flow through the Lagrangian point L towards the compact object, creating an accretion disk and finally accreting on the compact object. For the high mass X-ray binaries, the companion star is a massive companion star. It has a mass that is higher than 10 solar masses. And in general, it's an early type star of spectral class O or B. So due to the size, they are bright sources and can be detected also in the optical band. But for these binary systems, the accretion is different. The compact object accretes directly from the stellar wind emitted by the companion star. So stellar winds are fast winds and with typical terminal velocities up to 2,400 kilometers per second. And the companion star emits radiative line-driven winds. They are not homogeneous. In fact, they present strongly dense and highly perturbed areas or clumps. So if you ask yourself, how is the stellar wind? How can I imagine the stellar wind? How it is? So we can have a look to this 2D simulation made by Drissen. Here we have the stellar companion star surface and the emitted stellar wind. So till a certain point, till a certain distant radius, we have more or less the same density. But at a certain point, we have an inhomogeneous wind showing overdense and underdense regions. So with low densities in blue and high densities in red. But in my work, I focused on one particular source, Cygnus X-1. So Cygnus X-1 is a black hole X-ray binary, which is located in the Cygnus constellation. You can see here, it's more or less its position in Cygnus. And if you ask yourself, where is Cygnus in the sky? During summer nights, you can find Cygnus above your head. It was discovered as an X-ray source in 1964 during a rocket flight, while its radio emission was detected only later, in 1971. And Cygnus X-1 is also famous because it was the subject of a bet between the two astrophysicists, Stephen Hawking and Kip Thorne, regarding the nature of the compact object. In fact, Stephen Hawking thought that Cygnus X-1 was composed of a neutron star, so the compact object was a neutron star, while Kip Thorne thought about a black hole. At the end, Stephen Hawking was convinced by Kip Thorne, or he convinced himself, that the Cygnus X-1 was contained a black hole. And Kip Thorne won the bet. But let's talk about physics. So Cygnus X-1 is perhaps the best studied X-ray binary and one of the brightest persistent X-ray sources. It is composed of a black hole of about 21 solar masses and a companion star, a blue supergiant of about 40 solar masses. And although it doesn't show dramatic outbursts because it's a persistent source, it shows variability. And as every luminous black hole binaries, it shows two main spectral states, a hard and a soft. In fact, Cygnus X-1 goes a transit from one state to another, changing its variability and spectral properties. let's have a look at the energy spectrum. So during the soft state, the X-ray emission is produced in the optically thick, geometrically thin accretion disk, corresponding to a multicolor black body emission, which is dominating the energies below 10 eV. Well, during the hard state, the X-ray spectrum is dominated by Comptonization. The Comptonization is due to photons, thermal photons, or produced in the accretion disk, or synchrotron photons produced in the inner accretion flow, scattered by this hot cloud of hot electrons, that namely it's called hot corona, and it's located close to the black hole. When we look at the variability in terms of power spectrum, we can say that in the soft state is characterized by a low level of X-ray rapid, so from tens of seconds to milliseconds variability. With low levels, we mean that the root mean square amplitude is lower than 5%. On the other hand, the hard state is characterized by high levels of X-ray rapid variability, with a root mean square amplitude of higher than 30%. And we can see that we have a complex distribution of power variability over frequency. And we can say that the power spectrum in the hard state can be described by these two broad components, showing this particular double hump shape that phenomenologically can be modeled using two Lorentzians. But what are the effects of the stellar wind on the variability and on the energy spectrum, on the emission? So depending on the position on the black hole along the orbit, part of the X-ray emission will be absorbed by the stellar wind material. So here I'm showing you three different situations and the corresponding spectra that I've simulated. So when the amount of the stellar wind material between the observer and the black hole is minimum, the emission is not absorbed. But when the density increases, the emission starts to be absorbed. In the extreme case, when a clamp is between the observer and the black hole, the emission is strongly absorbed, leading to those events that we called dipping events in the X-ray light curve. Such events primarily occur at superior conjunction, or in other words, when the orbital phase is zero. And the wind absorption features can vary on short time scales. We are talking about of the order of minutes or shorter. And the effect of absorption is stronger during the hard state. Moreover, the wind variability can affect the observed variability of the source. So for my project, I had the idea to investigate how the variability of the stellar wind influences the X-ray spectral timing properties of the source. To do so, I used one monitoring being part of this peculiar campaign that is called Box, standing for Cygnus X-1 hard state observations of a complete binary orbit in X-rays. So this campaign had several purposes, and among them, one scope was to study the effect of the stellar wind and the stellar wind properties for Cygnus X-1 in its hard state. The Chalkbox campaign has as a primary instrument XMM Newton, but also it has simultaneous coverage made by NuStar, Integral, and also the very long baseline array. In my work, I used the long Newton monitoring, covering about 1.5 orbits of Cygnus X-1 in its hard state. This monitoring is composed of 4 different observations. And here you can see on the right, the orbital phase coverage for this monitoring. So the first observation is the 201 that you can see in purple, then the 501 in green, then the 601 in yellow, and the 701 in red. So as you can see, this monitoring is really peculiar because it covers 2 passages at superior conjunction, position along the orbit where the effects of the stellar wind are the strongest. But in order to study them, the effects of the wind, we have to distinguish between the intrinsic variability and the variability due to the stellar wind. How can we do this? We can say, okay, let's look at the light curve of the monitoring and select the dipping events. So here I'm showing you the light curve of the entire monitoring for a soft band in the upper panel, a hard band in the middle panel, and in the lower panel, the bottom panel, I'm showing you the hardness ratio computed between the 2 bands. These red lines indicate the passages, yes, a superior conjunction. So as I said before, the stellar wind affects first the soft energy band. So let's look at it. We can see, for example, here that we have dipping events, but when we look at the other energy band, the hard band, we don't see these dipping events. And as a result, we see an increase of hardness. So we cannot constrain these intervals as affected by wind absorption for sure. So 2 light curves are not enough to select those events affected by wind absorption. A powerful method is to look at the time-resolved spectral behavior of the source using color diagrams. So here I'm showing you the 4 color diagrams, one for each observation, that I computed for each 10-second data segment using 3 light curves in the corresponding energy bands, which define 2 colors, a hard color and a soft color. So when a clamp crosses our line of sight, color values change, given this particular nose track shape in these diagrams. So when the column density of the absorbing material is minimum, the emission is not absorbed. And we are in the top right part of these diagrams. But when the column density of the absorbing material is increases, the emission is absorbed. And we are in the bottom part of the diagrams. So, sorry, thanks to the color diagrams, I was able to select those events that are not affected by wind absorption, that from now on, I will indicate with NWA in green, NWA standing for not wind affected intervals. So now it's time to show you my main results, the main results of my analysis. So first of all, I will talk about the power spectra. Then I will give you a brief overview about the spectral timing techniques and what we mean when we say spectral timing. And I will show you then the 2 particular analyses, the time lags and the intrinsic coherence as a function of frequency. Of course, these are just the main results of my analysis. So if you want to know the details, you can have a look at my paper that was published last March in MNRAS. And of course, I'm here to answer to every question, to all of your questions. So let's have a look at the power spectra. Here, I'm showing you the power spectra for the first observation, the 201, which is the most absorbed, the more absorbed. and for the second observation, the 501, which is less absorbed. So the 201 is more absorbed because it corresponds to a passage at superior conjunction, while the second one, the 501, is less absorbed because it corresponded to an intermediate orbital phase. For 3 different energy bands. In blue, I'm showing you the power spectra for the total observation, the whole observation, while in green for the selection, the NWA selection, not wind-affected intervals. So although we don't see any particular difference for the power spectra for the less absorbed observation, we see differences in the power spectrum shapes for the more absorbed, and not only in the softest energy band, but also in the 310 keV. In particular, the stellar wind strongly suppresses the high frequency variability, smoothing out the typical double hump shape of Cygnus X-1 in its hard state, while the stellar wind enhances the low frequency variability. So for clumping with models, this increase at low frequency of power variability at low frequencies is due to the fact that when a clamp crosses our line of sight, the column density of the absorbing material increases. But these models cannot explain such a suppression at high frequencies. So we think that this suppression is related to scattering of emitted photons, changing time of arrival at the observer. Also, such a suppression requires a high optical depth that is not relatable to the stellar wind itself, but most likely to an optically thick region that we think is located at the impact zone of the stellar wind with the outer edge of the accretion disk. So, in fact, the optical depth of the scattering medium is inversely proportional to the frequency at what we see the suppression. So if we consider a scattering medium of this size as inferred by Zjarsky et al. In 2010 for Cygnus X-3, and we consider the frequencies at which we see the suppression, we are able to calculate the optical depth of the scattering medium, which is between 0.5 and 1, value that is way higher than the optical depth typical for the stellar wind. Previous studies on Cygnus X-1 related this scattering medium with an accretion bulge. So in order to further test this hypothesis, we made an additional analysis. So we select 2 consecutive time intervals close to superior conjunction, one outside a dipping event in purple, and one inside a dipping event in orange. And we constructed the power spectrum. Here, I'm showing you also the power spectrum for the not wind affected selection for the second observation, which is less absorbed, in order to visualize the double hump shape. But this double hump is suppressed in both inside and outside the dip, meaning that this suppression cannot be related to the clamps, to the passages of clamps, but it has to be related to an accretion bulge. Another important estimate we were able to make is the radial size of a typical clamp crossing our line of sight. If you look back at the power spectra I showed you before, you can see that at a particular frequency, the power variability for the total observation and the not wind affected selection is the same. This means that above this frequency, the stellar wind cannot introduce any additional variability. And for clamping with models, This frequency corresponds to the typical timescale of a clamp crossing our line of sight. So if we assume a wind terminal speed of 2,400 kilometers per second, we are able to calculate, to estimate the radial size of a typical clamp. So now I wanted to show you this overview about spectral timing. So what we mean when we say spectral timing, this complicated name, and what are the main spectral timing techniques analysis. So spectral timings, the spectral timing techniques are a class of analysis tools that find a connection between the variability in different energy bands. Born more than 20 years ago, these techniques have been widely used for different astronomical cases, not only X-ray binaries, but also with different scopes, with different purposes. But why are spectral timing techniques so important? Because understanding the causal connection between the different emitting regions is the key in order to unveil where variability is produced and how it can be transferred from one region to the others. But what is the fundamental element of these techniques? It's the cross spectrum. Let's consider two equally sampled time series, so two equally sampled light curves here in two different energy bands. And let's compute their Fourier transform. That the cross spectrum can be defined then using this formula. And using the cross spectrum, we can compute all these spectral timing techniques, such as, for example, the coherence as a function of frequency, but also as a function of energy, as well the time lags as a function of frequency or as a function of energy. Also, we can compute the covariance spectrum, the frequency result spectrum, etc. But in my work, I focused more on two particular spectral timing techniques, the coherence and the time lags as a function of frequency. So let's see these deeply. So the coherence measures the degree of linear correlation between two time series in two different energy bands as a function of Fourier frequency. When we say intrinsic coherence, we mean with this intrinsic, we mean that is the coherence intrinsic of the source. Here I'm showing you as an example, the coherence computed, the intrinsic coherence computed by Novak in 1999 as a function of frequency for Cygnus X-1 in its hard state. He computed the coherence between a disk-dominated band, this 3.9 keV, and a primary hard comptonization component-dominated band, this 8.2, 14.1 keV. And as you can see for Cygnus X-1, but also it is well known that in the hard state of black hole X-ray binaries, the primary hard comptonization component and the disk vary in a linearly correlated way, showing high levels of coherence, of intrinsic coherence on a broad range of timescales. The time lags are delays between flux variations in the two energy bands, so in the two time series, as a function of Fourier frequency. As before, I wanted to show you an example of Cygnus X-1 in its hard state. Here again, it was computed by Novak, but this time in 2000. And Novak computed the time lags between hard comptonization component dominated band 813 keV relative to a disk disk band dominated, to 4 keV as a function of frequency. And we can see that there is a particular trend, and this can be roughly approximated with a power law of a slope 0.7. But the important thing is that this slope presents particular features, step-like features, that correspond to the different Lorentzian features that I showed you before in the power spectrum. In general, black hole binaries present 2 different types of time lags. Hard, or in other words, positive lags, or soft negative lags. So hard lags, we find this usually at low frequencies, and they have a high amplitude, indicate that the rapid variability in the hard band is delayed with respect to the soft one. And they are interpreted as inward propagation of mass accretion rate fluctuations in the accretion flow. Soft lags, on the other hand, are negative. They appear usually at high frequencies, and their amplitude is small. And they indicate that the softer photons are delayed with respect to the hard ones. And they can be ascribed, and they can be explained, ascribed to reverberation. What we mean with reverberation. To properly understand this word, what does it mean? What it means, let's have a look at this cartoon that I made, underline the main spectral components of a black hole X-ray binary, the hot corona and the cold accretion disk. So as I said before, the hot corona dominates the hard band, while the accretion disk, the cold accretion disk, dominates the soft band. And for a black hole X-ray binaries in the hard state, usually we have a primary direct variable emission, but also a secondary emission due to hard photons that from the hot corona are backscattered to the disk and then reprocessed. So the additional time needed to this hard photons to travel this additional path, light path, introduced a time delay between the 2 fluxes. So defined as this, time lags can be converted into absolute distances, providing a direct diagnostic of the geometry of the hard X-ray source and the inner accretion disk. So I gave you just a general idea, a general overview of how powerful the time lags and intrinsic coherence as a function of frequency can be used for to constrain the geometry, for example, of these systems. But now I wanted to show you the main results of my analysis, and I want to highlight how these techniques are powerful also to constrain the properties of absorbers. In this case, of the stellar wind, the absorber in Cygnus X-1. So the first step in such analysis is to identify the energy bands that we want to use for our spectral timing analysis. So in our case, we wanted to use a corona-dominated hard band, yes, and a disk-dominated soft band. So we needed a spectral analysis. So here I'm showing you the spectra of the entire monitoring. Sorry, it's a little bit complicated. So I used a simple model to disentangle the single spectral components. So you can see that there is here the accretion disk in ... dash. Then we can see a hard comptonization components in dashes and its relative reflection component, dash dots, and also a softer quantization component. This component is required in the Cygnus X-1 spectrum because Cygnus X-1 has this soft excess component of unknown origin. So you can see that the accretion disk dominates energies lower than 1 keV, while the hard quantization component dominates energies above 2 keV. So for our analysis, we decided to use as a hard band the 210 keV, while for the soft band, the 0.31 keV. Also, for this analysis, we decided to focus more on the first observation of the monitoring, the 201. This is because this choice was dictated by the fact that the 201 is the most absorbed observation in the entire monitoring. And to further constrain the effects of the stellar wind, we also made another selection, this time comprising of the most absorbed intervals that from now on I will indicate with the nomenclature DIPS and in the magenta color. So the first result I wanted to show you is the intrinsic coherence as a function of a frequency computed between the two energy bands I showed you before, disk dominated and hard quantization dominated. So in blue, I'm showing you the intrinsic coherence for the total observation, in green for the not wind affected selection, and in magenta for the DIPS selection, the most absorbed ones, intervals, sorry. So as you can see, without the wind, the intrinsic coherence is very high, with values of 0.95 at the lowest frequencies, in agreement with previous studies of Cygnus X-1 in its hard state, as I showed you before from the Novak intrinsic coherence. But when we consider the stellar wind, it strongly suppresses the intrinsic coherence, and we think that this suppression is related to nonlinearity of absorption variability between the two energy bands. As last but not least, I wanted to show you the time lags as a function of frequency, computed again between the same energy band I showed you before, disk dominated and hard quantization component dominated. For in blue, I'm showing you the lags for the total observation, in green for the not wind affected selection, and in magenta for the DIPS selection, the most absorbed intervals. And as you can see, for the total and the not wind affected selection, we have hard positive lags, meaning that the rapid variability, the X-ray rapid variability in the hard band is delayed with respect to the soft one. But when we look at the DIPS selection, we see that the stellar wind introduces a soft negative lag. And we think at the lowest frequencies, yes. And we think that this soft lag is due to large-scale scattering within the wind itself, some kind of a reverberation inside the wind. And it becomes, this effect becomes the strongest when the continuum is strongly absorbed. So to conclude, these are the summary of, this is the summary of all my results. So from the variability study, we can say that the stellar wind changes the variability up to 10 keV. We can say that the stellar wind at low frequencies enhances the variability, and this is due to variations of the column density of the transiting clamps, while at high frequencies, the variability is suppressed. And we think that this suppression is due to scattering of emitted photons changing the time of arrival at the observer. Moreover, we were able to recognize the scattering medium as an accretion bulge, and we were able to make an estimate of the radial size of a typical clamp crossing our line of sight. From the spectral timing analysis, we can say that the intrinsic coherence is very high without the stellar wind, and the presence of the stellar wind strongly suppresses the intrinsic coherence. Also, the stellar wind introduces at very low frequencies, modulating the lag for the total observation, the amplitude of the lag amplitude for the total observation. And we think that this soft lag is due to large scale scattering within the wind itself. And for me, that's it. Thank you for the attention.